In this module, we're going to see the different shapes of orbitals. That's pretty much all. Yeah, it's good stuff. So starting out with an s orbital, that is the orbitals that are in an s subshell. Remember, we have an s subshell at every end from 1 on up, and it just looks like a sphere if you look at it from the outside. Remember the radial probability distribution function that I showed you? If you rotated that about 3 axes, x, y, and z axes, you get this. A couple things about this. The 2s subshell, the 2s orbital in the 2s subshell is larger than the 1s, and the 3s is larger than the 2s. If you were to look inside of these orbitals, for the 2s you would see one what we call node. For the 3s we would see 2 nodes, and as you probably figured out from the 4s we'd see 3 nodes, and so on. A node is a region of space where there's a 0 probability of finding the electron. Remember, we get these by taking psi squared, the wave function squared, giving us the probability of finding an electron in this given region of space. So the other thing is that on every atom, remember, every atom, all of these orbitals, subshells, and shells exist. Doesn't mean there are necessarily electrons in them, but they're there. So every orbital, for instance, has a 1s, a 2s, and 3s, all centered on the nucleus, all outside of each other, all sort of interweaving with each other. The thing is, they don't really interact, not very much with each other. An electron in these, like say an electron in a 3s orbital would not interact appreciably with an electron in a 1s or a 2s orbital. So those are the s orbitals and the s subshells. In a p subshell, we have every p subshell has 3 p orbitals. For example, in the n equals 2 shell, there is a 2p subshell that has 3 orbitals. We don't really worry about too much these sublabels px, py, and pz. They're derived from which axis the orbital lies on. This orbital lies on the x-axis, so we call it px, 2px. This one on the y, 2py, 2pz, etc. But the important things are that there are 3 orbitals in every p subshell. They are all perpendicular to each other, as you can see from here. They're all 90 degrees to each other, and they have phases. This plus and the minus represents like the phase of a wave, a node or a trough. And later on, we're going to talk about overlapping phases and orbitals, and we can get constructive and destructive interference. We'll do that later. There's a node here. Maybe you can see it best here, but right between these 2 lobes, this is one orbital, but right in between them there's a node where there's a 0 probability of finding an electron. It's like that for each of these p orbitals in this 2p subshell. In a d subshell, there are 5 orbitals. They look like this. We're not going to worry about these subscripts, dxz, dyz, dxy, etc. But basically, the important thing is there are 5 of those. 4 of them are similar to each other. 1 of them looks odd. And in an F subshell, remember the first time we see an F subshell is at the n equals 4 shell. There's a 4F subshell that has 7 orbitals in it, and they look like this. Pretty funky, but cool. Now, the thing about all of these orbitals in each of these subshells is that every 2p orbital in a 2p subshell is at the same energy. They're what we call degenerate. Degenerate means they have the same energy as each other, same energy level. Again, all 5 d orbitals in a d subshell are degenerate. They have the same energies as each other, and the same with the f orbitals in an f subshell.